Hi everyone, I'm Sui. I'm a first year PhD student at the University of British Columbia, and today I'll be presenting our work titled Secure Namespaced Kernel Audit for Containers. Now, how do things look like in the cloud? In Kubernetes, for example, pods are the smallest deployable units you can create or manage. So to run your workload, you'll be placing one or more containers into the pod, and each pod is isolated from each other. Now imagine something suspicious is happening in your container. You need some sort of information about the system to figure out what's going on. Now there are several ways we can do this with system auditing. The first one is what's commonly used by security systems, and that is host audit tools such as Linux Audit Framework. The way it works is fairly straightforward. Basically, the kernel component receives system calls from user space applications, and it filters them and passes them to the audit daemon that then generates the log. Now, because it uses system call interposition, it is not guaranteed to capture the complete system activity. So when you use the logs from this kind of tool to do security analysis, it's likely going to affect your results. Another alternative is reference monitor based audit tools such as Kernel and high-fidelity. So on a high level, this is how it works. Whenever a user space process is about to create, access, or delete a kernel object, it will trigger the LSM hook on the code path, and that in turn invokes a policy engine that captures information flow according to whatever the policy specifies. After that, the information will be passed to the user space daemon where the logs are generated. Now, compared to the previous host audit tool approach, this approach captures a more complete picture of system activity, so it is more suitable to be used with security analysis tools. And recently, there's an extension to the eBPF framework called BPF LSM that allows user-defined eBPF programs to attach to LSM hooks in the kernel. Basically, this is how it works. So developer writes eBPF programs in C, and that program can do things like auditing, for example. So eBPF program gets compiled into eBPF bytecode using a Clang compiler. And in the kernel, the verifier makes sure that your eBPF program doesn't cause any harm to the kernel. And then it will get JIT compiled into native assembly code and attached to the LSM hook. So whenever the LSM hook triggers your eBPF program in the kernel can interact with the user space daemon through some sort of data structure that is shared between the user space and the kernel, say the eBPF map. Now the benefit of this BPF approach is that with this, the tenant is able to specify audit rules to be executed in the host kernel. And because it uses Linux security modules too, they are also able to capture a more complete picture of system activity. There's also another extension to eBPF that allows BPF program to attach to cgroup hooks, but we won't discuss too much about this because that's mostly used for network filtering and network tracing, but not so much for system auditing. But the point here is that it is possible to namespace eBPF programs. Now, our goal in this work is to overcome the limitations in existing audit systems. So as you can see in the table here, we provide three features. First of all, our system is able to guarantee completeness in the generated log. So it is suitable to be used with security analysis tools like intrusion detection system or forensics. Now, a host audit tool doesn't guarantee completeness because it uses system call interposition, so it might miss some system interactions that doesn't go through the system call. And besides that, our system requires minimal host kernel modification, so it is suitable to be deployed in the cloud where host kernel modification is often forbidden. Reference monitor based audit tool doesn't provide this guarantee because to deploy a reference monitor based audit tool means that you have to add an entire LSM mechanism into the kernel source code. And finally, our solution supports policy specification at a container granularity. So this means that the tenants can specify audit rules for their containers. Now, besides the cgroup eBPF, the remaining three existing audit tools doesn't support this because they are deployed at a system level, so their audit rules apply to the entire system. In this paper, we propose saBPF, a lightweight and secure kernel audit system for containers. Combining the features we mentioned earlier, our system allows tenants to define audit policies for their own container and have them execute in the host system without having to modify the kernel at all. Now, how do we do this? So first, we use eBPF, a Linux framework that allows users to extend the capabilities of a kernel to do things like networking, monitoring, or tracing without the need to modify the kernel source code or load any kernel modules. So this is what allows the tenants to define eBPF programs to be executed in the kernel without any source code modifications. And we also use Linux security modules, which basically is a Linux framework that provides a set of in-kernel hooks that captures all meaningful interactions between kernel objects. Now, research has shown that LSM guarantees completeness so with this, our system can be used for security analysis. We also use cgroup namespace that isolates resource usage in a hierarchical fashion. Here's an overview of saBPF. Let's take this diagram as an example. So on the right, let's say that our system has two Kubernetes pods, and on the left, we have a user process trying to open a file, so that triggers the file open LSM hook. Now in saBPF, tenants write eBPF programs, and we attach those programs at the intersection of cgroup and LSM hooks. This means that when the file open hook is triggered, it doesn't just invoke all the eBPF programs attached to the hook. Instead, it will check the cgroup membership of the current task that triggered the hook. And let's say the cgroup membership of the current task is pod 1, container 1. So that will only invoke the eBPF program in that container. And because we're using cgroup namespace, saBPF follows the rule of cgroup hierarchy too, meaning the child cgroup inherits programs from the parent cgroup. So the file open program in the root cgroup in this case gets invoked in the context of current container too. We demonstrate three use cases of saBPF. So first, we implement profBPF, a whole system provenance capture mechanism built upon saBPF. And we also use saBPF to do things like intrusion detection and access control. But unfortunately, due to time constraints, we will not be discussing the last use case, but the details of it is discussed in the paper. So very briefly, host system provenance records the causality between events, system events as a directed acyclic graph, as you can see here. Our first use case, profBPF, is built with saBPF to generate provenance graph. The way it works is also quite straightforward. So with saBPF, profBPF attaches eBPF programs to generate provenance graph elements. And then the graph elements are passed to a shared buffer, which the user space daemon then used to serialize the graph elements and generate the log. So what's the advantage of using saBPF? So with saBPF, profBPF can attach programs at the intersection of LSM hooks and cgroup. So that means that the provenance capture mechanism can be deployed at a container level. In our second use case, we'll be looking at provenance-based intrusion detection system, which learns system behavior from provenance graph. However, most provenance capture mechanisms are typically deployed at the system level. This means that the intrusion detection system has to be deployed at the system level too, so the tenants cannot deploy their own intrusion detection system for their own containers. So to allow that, we use Kubernetes sidecar design to enable intrusion detection at a pod level. The Kubernetes sidecar design basically means that in your Kubernetes pod, you can run a sidecar container alongside your main application container. So this design allows us to add to an existing application without modifying it. In our case, we add a sidecar container that runs both profBPF and Unicorn, a provenance-based intrusion detection system, to a pod that can be running anything like database or web server without modifying it. So this way allows us to deploy our intrusion detection system provenance in the modular way without affecting the main application. Here's how it works. So in the sidecar container, profBPF audits the entire pod and generate pod level provenance graph. The provenance graph is then used as input to Unicorn, the intrusion detection system. And again, the advantage of using saBPF here is that the tenants can deploy intrusion detection system for their own parts. We compare the overhead of LSM, LSM-BPF, and saBPF invocation mechanism. And since saBPF is built upon LSM-BPF, so if we compare the red and the green bar, we see that the overhead of namespacing is constant for all system calls. Now, the overhead might seem significant here, but if you compare that to the overhead of SE Linux policy evaluation, we argue that this is acceptable. And in the macro benchmark, we compare the performance of our system against a host-based provenance capture mechanism called CamFlow. And we note that the overhead of namespacing doesn't cause significant impact to our performance, and instead our system still outperforms existing provenance capture mechanism. To summarize, saBPF has an improved performance because saBPF configures audit rules during eBPF compilation, so that overhead doesn't add into system execution. And saBPF also has a better maintainability because the mechanisms built upon saBPF is separated from the kernel, so it can be tested or built independently. And saBPF also supports decentralized deployment. This means that each container can deploy their own LSM mechanisms, audit policies without affecting the rest of the system. Thank you very much for your attention. Our project is open source and is available at this GitHub repo. And if you have any questions, please feel free to contact me. Thank you very much.